So this is going to be chapter 4.1 through 4.3 for Chem 1211. So we're going to start in chapter 4. This is all about chemical bonding. We're going to talk about 3 different types of bonding and then 3 different types of compounds that we're going to learn how to write and name their formulas in chapter 4. So first, the 3 different types of bonding that we're going to be looking at are ionic bonding, and how we know we're dealing with ionic bonding is typically metals and nonmetals. Typically, there is an exception to this rule, which we'll talk about a little bit later. Electrons are transferred in an ionic compound. The point of bonding for ionic and covalent compounds, metallic is a little different, but the whole point of bonding is the octet rule. So this means that elements are stable with 8 valence electrons. And so when we're bonding, we are trying to do our best to somehow exchange electrons or share electrons to get 8. For ionic bonds, we're going to transfer electrons. So we're going to exchange electrons. So for example, if potassium gets rid of an electron, it now is isoelectronic with argon. So potassium's looking to lose an electron. Chlorine, if it gains an electron, is isoelectronic with argon. And the reason why I'm saying isoelectronic with argon is because who has 8 valence electrons? Noble gases. So we want to be isoelectronic with noble gases. If we can help it. That's just one way. I mean, there's other ways to, you might have something with 8 valence electrons that it's not exactly isoelectronic with noble gases, but for the most part, what we're going to be talking about in this class, if you are bonding to get 8 valence electrons, you're most likely isoelectronic with noble gases. And I'll just say mostly here, because there are lots of ions that are not isoelectronic with noble gases, but I think it's helpful for your beginning understanding to think about it that way. So if chlorine is looking to gain and potassium is looking to lose, they'll just transfer electrons. So potassium's electron will just go to chlorine, leaving potassium positive and chlorine negative. And the reason why they stay together is because one is positive and one is negative, and now they have this opposites attract relationship, and they'll stay together. They stay together in this crystalline form, which you will probably talk about if you keep going in chemistry and talk about inorganic chemistry. And then you'll see this, usually you'll have solids. So ionic compounds are usually represented as solids. I don't know of any in room temperature that are liquids, because they're very, very strong forces that hold them together. So they are solids at room temperature, and a lot of them are crystals. So they'll be crystalline solids. Then we have covalent. Covalent bonding is between metals and nonmetals and metals. This is nonmetals and nonmetals, sometimes metalloids. Sorry about that. That really broke my brain. Sometimes metalloids. Metalloids are also sometimes involved in ionic compounds, but we usually see them hanging out with covalent. It just kind of depends. They're sharing electrons, so we're not transferring electrons. We said, hey, we're going to share. We're going to talk way more about this a little bit later, but we're sharing electrons here and forming a covalent bond. And you'll see that this one, for example, is bromine. So we would write this formula as Br2. We'd write this formula as KCl. For every 1 K, there's 1 Cl. It's a 1-to-1 ratio. We'd write this formula as Br2, showing there are 2 atoms of bromine in this one molecule. Bromine is actually a liquid at room temperature, but it quickly evaporates into a gas. You can see the liquid in the bottle there. And then we have metallic bonding. This is where we have that delocalized electrons between metals. We're not transferring, we're not sharing. Electrons are just kind of hanging out wherever in the whole thing. This is how metals are really good at conducting electricity. It's because their electrons can just kind of move through the metal. So we're really not going to talk too much about metallic bonding. We're going to focus mostly on ionic and covalent. So for ionic compounds, we have to really consider electrostatic attractions. Opposite particles, opposite charges attract each other. And so electrostatic potential energy is used here. This is Coulomb's law for my physicist. Basically, you don't need to worry about the formula here, but basically the charge, so the charges are these Q's, and D is for distance. The thing in front is just a constant. So the electrostatic attraction, and we can think about this as the attraction, is directly related to the strength of the charges. So if this is a charge of +2 and -2, it has a much larger attraction than if it's just +1 and -1. And then we also think about the distance here. If the smaller the distance, the larger the attraction will be because it's on the bottom of the fraction. So if you increase the bottom of the fraction, you're going to decrease the value. So if we increase the distance, the less the attraction. If we decrease the distance, the greater the attraction. And so distance, when we're talking about that, we're talking about atomic radius. Size. Right? The distance between the charges. So between the ions. And this has to do with the atomic radius, so the size. So ionic bonds have a sweet spot of distance between the two charges. If they're too close together, then the protons of both will start to repel each other. If they're too far apart, we don't have enough attraction or no interaction at all. And so there's a sweet spot of distance between the two ions that gives us our lowest potential energy, essentially, and our greatest attraction would be at this point here. Don't worry about this graph too much. Just know that there's a sweet spot of distance, and when we're talking about the distance between ionic ions in an ionic compound, we really are talking about that sweet spot of distance there. The lattice energy is the energy that you get when you make an ionic compound from its ions in the gas phase. So we can kind of summarize this by the energy you get when you make an ionic compound from its ions. And yes, it's 1 mole, which is an amount, and then they're in the gas phase, but we're not going to get too heavy into this. So I also like to think about the lattice energy as the other direction. It's also the energy to put in to break apart the ionic compound into its ions. And it's still 1 mole of an ionic compound into its ions as gases. But we can simplify our understanding. It's the same number, it's just whether or not it's energy released or energy absorbed. But it's the same value. I think sometimes it's just easier for us to think about the energy we have to use to take something apart versus the energy we have to use when we make something, which is a little bit harder to visualize. So what do you notice with the lattice energy in the ionic compounds? Are there any trends? I want you to look at these compounds and think about that list of common charges, perhaps. I want you to think about 2 things. I want you to think about, let me add this here. I want you to think about charges. And I want you to think about size. And see if you can explain why the lattice energies have a certain trend, or do they have a trend? So if we look at lithium fluoride versus lithium chloride, the charges on both of these are both, if we look at lithium fluoride versus lithium chloride. Charge of lithium is +1, charge of fluoride is -1, charge of chlorine is lithium is +1, charge of chloride is -1. So the charges are the same. But if we look at them versus size, fluorine is smaller than chlorine and as far as atomic radius, which would be the same for ionic radius as well. So when it gains that electron, it'll still be smaller than the chlorine that gained an electron. So this is a greater distance between Li and Cl. So smaller attraction and thus smaller lattice energy. We see the LiCl lattice energy is a smaller number. Or don't think about it so much as far as negative. It's not negative energy. It's the energy released. It's like the change in energy. So if we think about these in absolute values, it's a little bit easier to understand. It's the this is the amount of energy that's released. So we make it negative because it's the change in energy goes down when we make that compound. So don't worry about these numbers as far as the negativity of them. Just look at the absolute value of them. So absolute value of this number and the absolute value of this number. So when we're looking at lattice energy and just thinking about ranking them, look at absolute value. So smaller lattice energy for LiCl because the chlorine is bigger, and if you're too big, you can't be close enough to have a stronger attraction. So LiF has a stronger attraction, therefore it takes 1,049 kilojoules per mole, which is just an amount of energy and amount of substance. It takes 1049 to break it apart versus 864 to break LiCl apart. All right, I want to now look at the bottom two. Let's compare MgO versus MgCl2. MgO has a 2+ charge and a 2- charge. Mg2+. We just look at the individual charges of each. I know you have 2 Cl's, but that's a -2, a -1. So with the charges, put this the same. So we're going to move to this. Now first, you should always look at charges if you're trying to rank lattice energy. First, let's look at charges, and then if the charges are the same, then we can look at size. So first, we're going to look at charges. The MgO has a higher lattice energy than MgCl2 because greater charge equals greater attraction, which means it's harder to pull apart, which means it has greater lattice energy. And remember, we're looking not at the value of the negative because we don't have negative energy. We're looking at the absolute value just to get the idea of a number. We don't have negative energy versus the absolute value of 2540. So really comparing the absolute values here. So if you have to rank something based on lattice energy, first you're going to look at the charges, then you'll look at size. Really quick, just to get it out of the way. Again, those metallic bonds are just a sea of electrons. Electrons just kind of flowing around. So if it asks you what type of bonding is a sea of electrons, or electrons are completely mobile, you would say metallic. With covalent bonding, excuse me, with covalent bonding, we have 2 atoms with one or more pair of electrons that are being shared. And again, we have that same kind of idea for this bond length, distance between particles. Too far away, we're not sharing anything, and we come together, we start sharing. Here we have this perfect low energy attraction between particles, and then we have the nuclei get too close together if they move closer together. So we have a sweet spot. We call this, this is where we get the bond length from. And so it's that sweet spot, that distance when we get that low energy there. The bond energy is the energy that you need to break the bond. And so if you get to put in energy to break a bond, you also get out energy when you make a bond. So we'll talk a little bit about that. We'll get more into that in Chem 1212. But the strength of a bond is dependent on the type of bond it is, and then the polarity of the bond, which we'll talk about later. Right now, actually. So you can have chemical bonds that are shared, but sometimes they're shared unequally. So a shared pair of electrons is not necessarily shared equally. For example, Cl2, we can see these electron density map. If there's a lot of electrons in an area, it'll be a warmer color. If there's not a lot of electrons in an area, it'll be a cooler color. So we can see here the Cl2, it's kind of all the same color all around. This means that the Cl2 is sharing really well with itself. So this atom is sharing electrons really well with this atom, and you can think about those shared electrons as kind of just going back and forth between both atoms equally. We call this a nonpolar covalent bond because it's being shared equally, so even charge distribution. So electrons shared more equally. And I will say not entirely equally because there's a range, but shared more equally. If we look at this one, the next one, HCl, you see that we're starting to get a little more of this cool color, which means the H side is a little electron poor. So if there's not a lot of electrons, you're going to be positive. Now this symbol means partial. So we're not talking about a whole charge like this. We're talking about like a little bit more positive, but not a full ion. We put this little symbol, which is a Greek baby delta, and we'll say positive after it to indicate partial positive. So this is also partial negative on the other side. So the H is a little positive, the Cl is getting a little orange, it's a little negative, so partial positive, partial negative here. This is a polar bond. It's uneven. The electrons aren't shared equally. Chlorine is kind of hogging all the electrons, and hydrogen gets them only. Sometimes hydrogen will have electrons floating around it, but chlorine is going to take most of the electrons over here. So this makes this polarity where one side is positive and the other side is negative. It's not a full positive and negative, it's just partial, but still. And then if you completely transfer electrons, notice that we have totally electron rich, totally electron deficient. So we go all the way from end to end. And we're talking about full charges now. So ionic compounds, we got full on charges, nothing partial about it. We actually probably have areas of nothing in the middle there. But this is a complete transfer of electrons, not even a little bit uneven, just totally opposite. The reason why this happens is due to electronegativity. So electronegativity is the measure of how an atom can attract electrons in a bond. The most electronegative is fluorine, and then you can see that the least electronegative is francium. So as we move towards fluorine, we get more electronegative, pull electrons more when we're in a bond. As we get closer to francium, we pull electrons less if we're in a bond. In fact, these over here, these metals, they don't really share at all. These are a lot of things that just do ionic, right? We know ionic bonding, and if we look at the things that do covalent bonding, they're all the things that have pretty high electronegativities relative to the metals that have really low electronegativities. There are scales of electronegativity values that tell you if the bond is going to be polar or not. You only have to use this for homework with the numbers. You're not going to have to use the numbers on the test. On a test, I would ask you like, who's more polar, OF or NF? If it's farther apart from each other, it's going to be more polar because the differences in how they pull electrons are going to be greater. We'll talk about this more in class. It'll help to have a visual. I'll do a little visual demonstration in class for you, so it'll help a little bit more. But just know that the farther apart they are, the more polar the bond between them would be. So the more different they are, the more unevenly they'll share their electrons. The more similar they are, the more evenly they'll share their electrons. So if the difference in electronegativity is less than 0.4, we call it nonpolar. If the difference is between 0.4 and 2, we call it polar. And if it's greater than 2, it's just going to be ionic. It's not even going to share. For this class, We can say a nonpolar bond is a bond between the two of the same element or CH. Now, if you're doing homework or something, use the numbers, use the chart, and go from that. But on a test or something, let's just simplify this, same element or CH. That's not true in general. There are more nonpolar bonds than that. Excuse me, but for this class, just to simplify things, we'll say that's not polar. And then for a polar bond, we will do the opposite, either two different elements, not ionic here, so make sure you're talking about covalent, because ionic is different, a metal and non-metal. So two different elements, not CH. So let's consider CH to be a non-polar bond. And that can help you just to figure out what we're going to be doing instead of memorizing all the possible non-polar bonds. So sometimes pure substances, we've talked about them dividing between elements and compounds if you watch the little preview for chapter 1, but you can have elements that exist as atomic or molecular. So molecular would be covalently bonded for compounds, or ionic would be an ionic compound. And then molecular elements are just elements that are bonded together. So O2 is a molecular element because they're sharing electrons with each other. Versus neon is an atomic element because it exists only in atoms. O2 exists as molecules, but each atom is exactly the same. That's what makes it an element. If we look at a molecule of water, you've got two different elements bonded together. So that's the difference. There are 7 molecular elements that I want you to know. They are diatomic. Diatomic meaning 2 atoms. Excuse me. So these are your 7 diatomics. I remember them by starting at number 7 on the periodic table. Make the shape of a 7. But if we count that, 1, 2, 3, 4, 5, 6, it's only 6, so we add hydrogen to make it 7. So 7, 7, 7. Or you can remember to break it down like this: have no fear of ice cold beer. So H, have, N, no, F, fear, of, O, ice, I, cold, C, beer, B. Or 777, however you want to memorize it. When they are alone or by themselves only. When these elements are alone, not bonded to another element. If it's bonded to another element, it's not alone. And it's not going to be diatomic. For example, H2O, the O is not diatomic. NaCl, the Cl is not diatomic, right? So the H is not diatomic in H2O either, if we look at the Lewis structure, which we'll use, I think we'll do that in another class. But just so you know, it's only when they're by themselves that they exist like this. So if I say my patient has a tank of oxygen, it's O2 in there. I'm breathing oxygen, it's O2 that we're breathing. Okay, we're going to end this video here. There's going to be one more video with this section. We'll talk about writing and naming chemical compounds. And I'll probably put that video together with this one, actually. So you may see it just continue in just a minute, or I may make it separate.